Hello everyone! Today we're introducing two functions that I invented. Now I'm actually pretty late to the Summer of Math Exhibition 3 competition. I just joined the Discord a few days ago, so I don't know much about latex and other things. Just a quick reminder, now let's begin. You need some calculus knowledge. I took Calc 2 in the summer, and it's through this class that I became motivated to do this research. If it wasn't for this class, I probably wouldn't have known the concepts as well. So I'm personally writing a paper about it. There isn't a specific goal to this project. Just let's see what we can do with this research with like-minded people. In high school, in pre-calculus, you might have learned that a sigma notation means the sum of some specific sequence, all the terms added together. With the pi notation, it's exactly the same thing except all the terms are multiplied together. So the main thing we're talking about today are two functions. Now, the first one of them is the null function. The null function takes the first how many ever m terms of a series sigma x sub n. It separates the first term with the rest in the series, and it multiplies the rest of the series by some number, let's say a. Here's an example. We take the first term of the series 1 plus 1 plus 1 plus 1, and we multiply the rest by 2, which gets us 1 plus 2 plus 2 plus 2. So for no subscript 2, we take the first two terms of a series and then separate it, multiply the rest by 2 again to get you 1 plus 2 plus 4 in this case. Let there be another function called the void function, where similarly takes the first m terms of a product, separates it from the rest, and adds a to the rest of the product. An example of the void function being applied is x factorial. It involves the void function being applied x times, hence the exponent. Now we'll get into that in a little bit. Onto a product of all ones, x ones to be exact. Now a equals 1. That means you'll have 1 times 1 plus 1 times 1 plus 1 plus 1, etc. Eventually it goes to x, which makes x factorial. Between the null and the void functions, the null function is the more frequent one and the more useful one. You can even get integers from just applying the null function to itself. 2 equals 1 plus 1 halves plus 1 fourths plus 1 eighth, etc., which equals the null function with step size 1 being applied n times. As n goes to infinity, 1 half equals a summation of 1, which equals 1 plus 1 times 1 half plus 1 times 1 half times 1 half. It's very similar to the factorial, except that you are multiplying a term of a summation instead of adding something to a term of the product. There are two things to be taken care of. The limit operator doesn't really look nice, so instead we'll be lazy and not go with the proper notation and go with, for example, no to the exponent of infinity later on, because it is applying to itself infinite times. It isn't really applying to itself n times strictly. It is applying to the portion after the summation sign. This will illustrate in equation form as no sub n of p, no sub n minus 1 of p, no sub n minus 2, etc., etc., until you get to no 1 of p, comma, summation q sub n, for any number or variable p and q sub n. with no sub 2 to the n instead, it will be no sub 2n of p, no sub 2n minus 2 of p, and so on. From the inside to the outside of the parenthesis, the function has an effect later and later and later, with the main properties of the no function and the void function in mind. Let's do something with it, shall we? We're first going to construct pi with the Wallace product below, then e to the x in a later slide. If we change the letter a mentioned before to some function f of x, the no function can describe many series by multiplying the function f of x onto, say, a series of all ones. We can make a lot of things from here. The Wallace product states that pi halves equals product from 1 to infinity of 2n over 2n minus 1 times 2n over 2n plus 1, which is the product you see here. Notice how the numerators increase by 2 per 2 steps of multiplication. The denominators increase by 2 per 2 steps as well, but is shifted one place left. This might have been hard to express, but if we take a look at the original form of the equation, you'll see that the order actually doesn't matter that much. The original form involves a summation of 4n squared over 4n squared minus 1, which is 2 times 2 times 4 times 4 times 6 times 6, etc. We can convert this to a staircase of step length 2 and step height of 2, which is 2 times 2 plus 2 times 2 plus 2 times etc., which equals this. The denominator is only 1 away, so it has a 1 instead of 2. And there we go, we have pi achieved using the void function and some other product that does not involve a variable. This might be more intuitive for the understanding of a finite or infinite series or product. Let's get to e to the x. In Calculus 2, there is a definition for e to the x using a power series representation. It converges for all x, which means essentially that the power series approximation is equal to e to the x itself for all values of x. There are 3 steps to it. We start with x to the n in a similar fashion than what we've seen before, then 1 over n factorial, which requires a variable as the a because it is essentially multiplying 1 over n, which depends on the value n, onto itself. So the best method I've found right now is just substituting a with a variable, say 1 over k right here. As the no function multiplies the nth next term and thereafter in a sum, the void function adds to the nth next term and thereafter in a product. We can get the 2 identities where no sub-zero of a and b equals a times b, and void sub-zero of a and b equals a plus b. Surprising, isn't it? This is essentially how the a turned into a variable f of x, for example, turns into the thing being multiplied or being summed. To multiply the 2 parts together, we simply combine them via a no sub-zero. Therefore, we have e to the x in what I think is very beautiful, a representation using the no function, the void function, a sigma notation, and a pi notation. And to this point, I start wondering, what can it not describe? When can differences between each individual terms not describe a pattern? Is it really useful if we generalize everything together? A far more generalized notation for repeating stair-like operations, which I'm working right now, contains 5 elements. The sides of each step, gap size between each repetition, how many times the function repeats, the function itself, the factor of modification, and finally the domain that is being modified. Now, that sounds a lot like a definition of a function with its domains, its range, what it does to a set of numbers that are in a domain. The notation can generalize every mathematical expression that I've thought of, which admittedly is not a lot. But where do we go from here? Can we pose a conjecture about whichever function or expression that cannot be obtained by the null, the void function, and this notation right here? And that is for us to decide another day. You might see a lot of graphics and animations in this project. The animations, I made them on Google Slides. The pictures, well, I actually took them in a trip a while back. These are what I used to make this video if you are interested to look them up. And bye, thanks for watching.